All right, we got two integrals to convert from polar to Cartesian and then evaluate. So for the first one, let's see, setting up the region, we've got r going from 0 to 1 and theta from 0 to pi over 2. So I recognize that right off the bat as being the quarter of the unit circle in the first octant, or first quadrant rather. And let's see, so we're supposed to set this up in terms of Cartesian. I'll do dy first, so we'll be integrating that way in the inside integral, and I guess we go from x equals 0 to x equals 1. And we'll be going from y equals 0 up to y equals square root 1 minus x squared. So we've got 0 to 1, 0 to 1 minus x squared. And let's see now for the integrand, I can write this as r cosine theta times r sine theta times r dr. And so this last r is going to be left over for being part of my Jacobian for polar. And we've got an x and a y and a dy dx. All right, now it's just a simple matter of integrating polynomials. So let's see, 0 to 1 x y squared over 2, 0 to 1 minus x squared, dx on the outside. So this is going to be, I can pull the 1/2 out in front, and we'll have integral 0 to 1 x, and then when I square that thing, 1 minus x squared dx. And so that's going to be an integrand of x minus x cubed. So when I integrate that sucker, I'm going to have, let's see, so I've got my lonely factor of 1/2 out in front, and then I'm going to have x cubed over 3 minus x to the 5th over 5. Oh, sorry, what am I doing? I went up 1 power too many for absolutely no reason. I have no brain fry. Okay, x integrates up to x squared over 2. And then we have x cubed goes up to x to the 4th over 4, 0 to 1. Okay, nice thing is at the lower bound of 0, both of those disappear. So this actually just looks like 1/2 times 1/2 minus 1/4, and 1/2 minus 1/4 is 1/4, and 1/4 times 1/2 is 1/8. The end. But wait, there's more. We still have part B. Okay. So for this one, let's see, we've got, this one's a little bit trickier. I'm going to have to figure out what to do with this one here. So I'll start thinking r equals 2 secant theta. Switch the secant over to the other side, and it becomes r cosine theta equals 2. And that one I recognize as x. Okay, so there's my equation for that one. So we've got x equals 2, and now let's see, and so we're going from r equals 0, so that's at the origin. So we're going from the origin to this line like this, and we're going up to pi over 4. So there's pi over 4. Okay, so we've got lines like this. Okay, so there's my region. So this one was pi over 4. So now I just need to set that up in Cartesian. I guess we can do dy first again. So then we're going to be going from x equals 0 to 1, and y is going to go from 0 up to y equals x. So I've got 0 to 1, and then 0 to x. Oh, sorry, my geometry is off. This is a 2. Okay, this one right here, that's a 2. So this needs to be a 2 over here as well. So we've got that. Okay, and then let's take a look at our integrand there. And so for our integrand, I've got r5 sine squared theta, which I can write as r sine theta quantity squared times r squared times r. Okay, and so this one here will be for my Jacobian, and that leaves me with y squared, and then r squared is x squared plus y squared dy dx. Alright, so then I can integrate, and my x squared, nobody cares about him. Y squared becomes y cubed over 3, and this is from now 0 to x. And then we've got y to the 4th becomes y to the 5th over 5. And that's also from 0 to x. And let's see now. Evaluating these guys, I'm left with integral 0 to 2 x to the 5th over 3 plus x to the 5th over 5. And then I guess I can combine those. And so we have, what is that? So that's like 1/3 plus 1/5. So we have 5, 3, 8 15ths. So we've got 8 over 15. And then I've got x to the 5th, which becomes x to the 6th over 6 from 0 to 2. So the bottom one drops out, and the top one is some gigantor number. So what? So we've got 2 to the 6th times 2 to the 3rd, so that's 2 to the 9th is 512. Cancel 1 in the denominator, and we have 256. And then in the bottom we have 15 times, I guess there's 3 left over from the 6, so 45.